So let's have example 5.11 first. So I arranged the examples so that they are arranged from simplest to challenging ones. So this is supposedly simply supported, but let's compute only the displacements. Those are the required, not anymore the reactions and member forces. So these are the effect of the fixed moment. Remember, we imagine that these are all fixed. So although this is an overhang, but there is a load here over the entire overhang. So we still imagine that this B here is fixed and C is fixed. So the effects of the loadings would be to produce these moments here. There are 4 degrees of freedom, 1 at A, 1 at D, and 2 at C. But because this is a problem for a quiz or an exam, you have to find a way to solve this using your calculator. And the calculator is limited up to 3 unknowns only, simultaneous unknowns only. So actually, we can do this by considering A, B only so that we have only 2 unknowns, rotation at A and rotation at B. So we first ignore BC, but we have to compute the moment in order to have a nodal force at B. The moment is equal to 30 times 2 times 1, and it should be counterclockwise, so that because the effect of the moment is of the overhang moment is clockwise. So again, 30 times 2 times 1, this is 60. Now let's reduce the 4 unknowns to just 2 by considering only AB. And we will have the effect displacement at C on later when we consider BC alone, after we solve for rotations at A and at B. So fixed moment AB is equal to fixed moment BA because the entire span AB is loaded. So WL square over 12, 36 square over 12 is 90. For the reactions, that's also the same, 1/2 of 6 times 30. So FA equals FBL equals 1/2 of 3, 1/2 of 30 times 6 or 90 kilonewton meter. MBC on the other hand is 30 times 2 times 1, 60 kilonewton meter. So that's 60 indicated in the figure. So at node 1, the fixed end force, which is due to rotation only, because that's a support, does not settle. So this is counterclockwise or clockwise, and it is equal to 90 clockwise. At B or at node 2, we have 90 minus 60, so positive 30. So 30 counterclockwise. So again, 90 clockwise minus 60 counterclockwise is equal to 30 clockwise, which is the net fixed end force. Because fixed end force and nodal force are opposite, so if it is 30 clockwise, then the opposite of 30 clockwise is 30 counterclockwise. So that's why this is 30 counterclockwise. So KEB is 12 over 12 times 1 over 6 cubed, and we already have experience about 12 over 6 cubed. You may cut and paste the stiffness of that member so that you don't need to fill up the rest. But if you are still not mastering how to fill in the cells, then do it religiously one by one until you can memorize it. And when you know already how to fill in these cells here, because of our experience, then you just cut and paste those cells with the same values. So because we only consider member AB, so these are the forces 1, 2, 3, 4. We are only interested of U2 and U4, the rotation at A and the rotation at B. So we shade columns 1 and 3 and rows 1 and 3 because they are associated with zero displacements. So therefore, U2, U4 can be easily computed as the inverse of this 2 by 2 matrix. Can you see it? The unshaded ones, 2/3, 1/3, 1/3, and 2/3 times the force matrix negative 90 and 30. So because you can easily do that with your calculator, and you just make it fast. Negative 210 over EI and 150 over EI. That corresponds to theta A and theta B. Now let's incorporate BC because we already found theta B. For BC, again, we consider this as fixed-ended. So because we have a load, then there should be fixed end forces. So this is the stiffness of BC. 12 divided by 2 cubed is 3 halves or 1.5. 6 divided by 2 square is also 1.5. Then a negative 1.5. Then copy 1.5. Copy 1.5 here. This is 4 over 2. 4 times 1 over length 2. So 2. Then negative of this value. Then 1 half of 2 is 1. Then the negatives of the first row here with in the cell. Then this is row 2 with columns 2 and 4 entries interchange. So if this is member BC, imagine that the ends are fixed. So there will be fixed end moments and reactions. So for the fixed end moment, we have W30 times 2 square over 12, the formula. That would be 10 kilonewton meter. Then FBR equals FCL, 1 half of 2 times 30, so 30. So that the forces for B and C would be 0. Global forces would be, you go back to the original one, so 0, 0, and we have FCL at C, which is equal to negative 30, because this is 30, that's the fixed end force. The nodal force, remember, is opposite to that fixed end force, so downward, negative 30. And we have here clockwise fixed end moment, which is 10. Remember, the nodal force at C is counterclockwise, opposite to 10. So that's why we have positive 10 here. Then, to solve for U5, U6, we again expand the last two rows. We call this row 5 and row 6. So we expand rows 5 and 6. For node 3, which is C, these are the loads 10 counterclockwise and downward load of 30. So that's why negative 30 and 10. But you can actually expand the upper two rows if you want. So let's just expand rows 5 and 6. So negative 30 times 10 times this matrix here multiplied by this given displacements. U4, by the way, is theta B 150. So negative 30, 10 equals negative 1.5, negative 1.5, 1.51 times 0, 150 plus 1.5, negative 1.5, negative 1.52 times U5, U6 matrix. So expanding and simplifying, the first force matrix here is negative 1.5 times 0. Negative 1.5 times 150 is negative. Transpose it to the left, it becomes positive. So negative 30 plus 1.5 times 150 is 195. Likewise, 1.5 times 0 is 0. 1 times 150 is 150. Transpose to the left, negative 150. So 10 minus 150 is negative 140. Then equals this 2 by 2 matrix times U5, U6. Solving for U5, U6 using your calculator, U5, U6, which corresponds to delta C and theta C, would be 240 and 110. So finally, for member AB, we only have values for U2, and we also have U4. So we shade columns 1 and 3. And the fixed end forces would be 90, FA 90, FBL 90. And moment is 90. On the right side is negative 90. So 1/6 times negative 210 plus 1/6 times 150 plus 90 equals 80. 2/3 times negative 210 plus 1/3 times 150 plus 90 equals 0. Of course, we expect 0 moment at A. And so on and so forth. So you get 100 shears at B just to the left and moment BA negative 60, which is the moment at B. And for BC, fixed end forces, we have, although we experienced an overhang before, but remember the load there was acting at the rightmost end. That's why we only have one fixed end force. But because this time the overhang has this load, then these are the fixed end forces. So FBR is 30, FC left is 30, which is this. Moment here is counterclockwise 10, so positive. Moment at the right side is clockwise, so negative 10, which is this. Then this is stiffness. We shade column 3 because U3 is 0. We only have U4, U5, U6 values. So it's computing and you have to verify that these are the results. So of course this is correct because we do not expect shear at C and moment at C is also 0. So I leave that to you to multiply this row matrix with this column matrix here and add the fixed end force and so on and so forth. So MB is negative 60 kilonewton meter and RB is shear just to the left 100 plus shear just to the right 60. So that corresponds to delta C and example 5.11 for the beam loaded as shown, find theta A, delta C, EI is constant. So this is the second way of solving this problem. So let's solve the problem directly as 4x4 matrix because there are 4 degrees of freedom. And to do that, so the unknowns are 4x4. We do not worry because this time we use Excel. So that would be FCL. So fixed end moment AB is fixed end moment BA, which is the same as before, 90 kilonewton meter. FA equals FBL equals also 90. Fixed end moment DR is 30 times 2 square over 12, so 10. They are equal. FDR equals FCL equals 1/2 of 2 times 30, so 30. So at node 1, the load here is, because this is counterclockwise, so clockwise. 90, negative 90 for its sign is negative 90. Node 2 is D, we have 90 and minus 10. So that would be positive 80, so counterclockwise, positive 80. And at node 3, we have FCL, which is 10, so that's the fixed end force, so the nodal force is 10 downward, negative 10. And we have a clockwise moment here, so the nodal load is nodal force is counterclockwise, positive 10. So we have 10 and downward load of 30. So these are the nodal forces. So KAB is equal to, just like before, let's just copy it. And KBC is 12 over 2 cube, 1.5, and 1.5, negative 1.5, and so on. It's the same as before. And for the entire general structural stiffness matrix, we have 2, 4, 5, 6 only. U2 rotation at A, U4 theta B, then U5 and U6. So that's why we have 2, 4, 5, 6. U2, U4, U5, U6, 5, 6. So this is 4x4. These are the forces. We can easily use Excel here to invert this 4x4 matrix multiplied by this force matrix here. So this is ABC so that you can see these are the global forces. Look at the result, it's the same. So in Excel, 8/3 is 2 and 2/3. You have nothing to do. That's the way Excel inputs this data here, as well as this negative 1.5. So as long as they're the same. So in this cell here, F2 to F5, this is equal to the the product or matrix multiplication of the inverse of this 4 by 4 matrix and this column matrix here. So the result will be this, which is similar results as in the preceding example, which we solved manually, and we use the technique of reducing it to just 2 by 2. So for the member forces, it will be the same. So moment at B is negative 60, and RB is 100 plus 60, so 160 kilonewtons. So that's it.